The 7th lecture video on temperature and heat will cover the expansion of solids. In general, most solids expand when heated and contract when they are cooled. They also expand and contract in all three dimensions, length, width, and thickness. When a solid is heated, the expansion is due to the increased length of vibrations of molecules. This results in expansion in all directions, like I just mentioned. As an example, thermostats operate on this principle. Thermostats have a bimetallic strip, usually steel and brass, in them. Different solids expand and contract at different rates, so when the thermostat is heated, the bimetallic strip bends one direction or the other, depending on which metal is located where. This difference in how the metal is heated will either close the circuit in the thermostat or open it, depending on if it is heated or cooled. Like I already mentioned, different materials expand at different rates. The amount a solid expands depends on the material, the length of the solid, and the amount of change in temperature. If we want to calculate linear expansion, which is just the expansion in one dimension, length, we can set the change in length equal to alpha times L times delta T, where delta L is the change in length, alpha is a constant called the coefficient of linear expansion, which can be found online or in a table, L is the original length, and delta T is the change in temperature. Looking at this equation, we can see that the longer the solid is initially, the larger the expansion. This is due to the fact that in a longer material, there are more molecules to heat and vibrate. Also, the greater the change in temperature, the greater the linear expansion. It doesn't matter what unit we use for L or delta L, as long as those two quantities have the same unit. Let's look at a linear expansion example. A steel railroad track is 78.0 feet long at 0 degrees Fahrenheit. How much will it expand when heated to 95.0 degrees Fahrenheit? First, we will write down what we were given in the problem statement. We know the original length L is 78.0 feet. We also know the change in temperature, delta T, is going to be the temperature difference between 95.0 degrees and 0 degrees. Subtracting, we see the change in temperature is 95.0 degrees Fahrenheit. Since we are looking at steel, we need to find the coefficient of linear expansion from a table, which is 6.5 times 10 to the minus 6th per degree Fahrenheit. In this problem, we are trying to find the change in length, delta L. The basic equation we will use for linear expansion is that delta L equals alpha times L times delta T. Next, we can substitute into our basic equation. Delta L equals 6.5 times 10 to the minus 6 per degree Fahrenheit times 78.0 feet times 95.0 degrees Fahrenheit. This gives us a change in length of 0.0048 feet, or, since it is hard to picture how long that is, about 0.58 inches. Next, we will look at area and volume expansion, since when heated, objects expand in all three dimensions. Sometimes we only care about the area expansion, but sometimes we also need to know the volume expansion. The area expansion, delta A, equals 2 times alpha times A times delta T, and delta V, the change in volume, is equal to 3 times alpha times V times delta T. Delta A is the change in area, alpha is the coefficient of linear expansion, which we saw in the linear expansion formula, A is the original area, delta T is the change in temperature, delta V is the change in volume, and V is the original volume. Let's take a look at one more example. A section of concrete on a highway measures 50.0 feet by 30.0 feet by 1.00 feet at 90.0 degrees Fahrenheit. What allowance for change in volume is necessary for the temperature to drop to negative 15.0 degrees Fahrenheit? First, we're going to go ahead and write down all of the information we know. We know the dimensions of the concrete is 50 feet by 30.0 feet by 1.00 feet, so this would give us an initial volume of 1,500 cubic feet. We can also find delta T, the change in temperature, by taking 90.0 degrees Fahrenheit minus a negative 15.0 degrees Fahrenheit. So that gives us a change in temperature of 105.0 degrees Fahrenheit. Alpha, the coefficient of linear expansion for concrete, is 6.0 times 10 to the minus 6 per degree Fahrenheit. And in this problem, we are trying to find delta V, the change in volume. We'll go ahead and write the basic equation next. Delta V is equal to 3 times alpha times V times delta T. Next, we can go ahead and substitute. Delta V is equal to 3 times 6.0 times 10 to the minus 6 per degree Fahrenheit times 1,500 cubic feet times 105.0 degrees Fahrenheit. This gives us a change in volume of 2.84 cubic feet. This concludes our discussion on linear area and volume expansion.